1.3.2 X.500, the Directory Server Standard. However, the OSI protocols did address issues important in large distributed systems that were developing in an ad hoc manner in the desktop and internet marketplace. One such important area was directory services. The CCITT created the X.500 standard in 1988, which became ISO 9594. Data communications, network directory, recommendations X.500, X.521 in 1990. Though it is still commonly referred to as X.500. X.500 organizes directory entries in a hierarchical namespace capable of supporting large amounts of information. It also defines powerful search capabilities to make retrieving information easier because of its functionality and scalability. X.500 is often used together with ad hoc modules for interoperation between incompatible directory services. Note: an accessed online resource on X.500 is the book Understanding X.500, the directory. While dated 1996, this book, which is now out of print but available online, is considered one of the original of the directory world. It describes and defines the X.500 directory model in great detail. Much of the material is still very much relevant in today's current family of LDAP directory servers. It can be found here: http://www.sai.salford.ac/wdwc/x500.htm. X.500 specifies that communication between the directory client and the directory server uses Directory Access Protocol (DAP). However, as an application layer protocol, the DAP requires the entire OSI protocol stack to operate. Supporting the OSI protocol stack requires more resources than are available in many small environments. Therefore, an interface to an X.500 directory server using a less resource-intensive or lightweight protocol was desired. 1.3.3 Lightweight Access to X.500. Lightweight Directory Access Protocol was developed as a lightweight alternative to DAP. LDAP requires the lighter-weight and more popular TCP/IP protocol stack rather than the OSI protocol stack. LDAP also simplifies some of X.500 operations and omits some esoteric features. Two precursors to LDAP appeared as RFCs issued by the IETF, Directory Assistance Service, RFC 1202, and Dixie Protocol Specification, RFC 1249. These were both informational RFCs, which were not proposed as standards. The Directory Assistance Service DAS defined the method by which a directory client could communicate to a proxy on an OSI-capable host, which issued X.500 requests on the client's behalf. Dixie is similar to DAS but provides a more direct translation of the DAP. The first version of the LDAP was defined in X.500 Lightweight Access Protocol, RFC 1487, which was replaced by the Lightweight Directory Access Protocol, RFC 1777. LDAP further refines the IDs and protocols of DAS and Dixie. It is more implementation neutral and reduces the complexity of clients to encourage the deployment of directory-enabled applications. Much of the work on Dixie and LDAP was carried out at the University of Michigan, which provides reference implementations of LDAP and maintains LDAP-related web pages and mailing lists. RFC 1707 defines the LDAP protocol itself. RFC 1777, along with string representation of standard attribute syntaxes, RFC 1778, a string representation of distinguished names, RFC 1779, an LDAP URL format, RFC 1959, a string representation of LDAP search filters, RFC 1960, defined the original LDAP version 2 version of the language. LDAP version 2 has reached the status of draft standard in the IETF standardization process. One step from being a standard, all of today's directory server implementations are based on the LDAP version 3 specification. LDAP version 3 is defined by Lightweight Directory Access Protocol. Version 3, RFC 2251, related RFCs that are new or updated for LDAP version 3 are Lightweight Directory Access Protocol version 3, Attribute syntax definitions, RFC 2252. Lightweight Directory Access Protocol version 3. UTF-8 strings the representation of distinguished names, RFC 2253. The string representation of LDAP search filters, RFC 2254. The LDAP URL format, RFC 2255. A summary of the ext.596 user schema for use with LDAP version 3. RFC 2256. Authentication methods for LDAP, RFC 2829. LDAP version 3. Extension for transport layer security, RFC 2830. Lightweight Directory Access Protocol version 3. Technical specification, RFC 3377. RFC 2251 is a proposed standard, one step below a Java standard. LDAP version 3. Extended LDAP version 2. In the following areas: referrals, a server that does not store the requested data can refer the client to another server. Security, extensible authentication using simple authentication and security layer, SASL mechanism. Internationalization, UTF-8, support for international characters. Extensibility, new object types and operations can be dynamically defined and schema published in a standard manner. In this book, the term LDAP refers to LDAP version 3, unless LDAP version 2 is specifically stated. Differences between LDAP version 2 and LDAP version 3 are noted when necessary. 1.3.4 Beyond LDAP version 3. Recently, the push for encapsulating LDAP operations within XML for use within web services has spawned a new language called the Directory Services. Markup language DSML. The most recent of the specification is DSML version 2. DSML is an XML schema for representing directory information. It's a generic import-export format for directory information. Directory information in DSML can be shared between DSML-aware applications without exposing the LDAP protocol. XML provides an effective way to present and transfer data. Directory services allow you to share and manage data and are thus a necessary prerequisite for conducting online business. DSML is designed to make directory service more dynamic by employing XML. DSML is an XML schema for working with directories. It is defined using a document content description, DCD. Thus, DSML allows XML programmers to access LDAP-enabled directories without having to write to the LDAP interface or use proprietary directory access APIs, and provide one consistent way to work with multiple dissimilar directories. More information on DSML can be found in Appendix A, DSML version 2 on page 655. Various directory integration technologies have emerged in recent years that utilize LDAP and directory concepts to decentralize and or synchronize data between disparate directories as well as other disparate non-directory data sources. Two of the more prominent technologies in this directory integration space are metadirectories and virtual directories. These technologies are covered in greater detail in Appendix B, Directory Integration, IBM Tivoli Directory Integrator, on page 681. 1.4 Directory Components. A directory contains a collection of objects contained in a tree structure. The LDAP naming model defines how entries are identified and organized. Entries are organized in a tree-like structure called the Directory Information Tree. DIT. Entries are arranged within the DIT based on their distinguished name. DN is a unique name that unambiguously identifies a single entry. DNs are made up of a sequence of relatively distinguished names. RDNs. Each RDN in a DN corresponds to a branch in the DIT leading from the root of the DIT to the directory entry. The DN is composed of a sequence of RDNs separated by commas such as TN Thomas, OU, it's so, O, IBM. You can organize entries, for example, after organizations, and within a single organization you can further split the tree into organizational units, and so forth. You can define your DIT based on your organizational needs as shown in Figure 1-2 on page 17. If you have, for example, one company with different divisions, you may want to start with the company name under the root as the original organization, O, and then branch into organization units. or U for individual divisions. In case you sort the data from multiple organizations within a country, you may want to start with the country, C, and then branch into organizations. For more information on planning on DIT, refer to Chapter 3 Planning Your Directory on page 57. Understanding of DIP design and implementation. Directory root up, OIBM CUS. Example of a directory information tree. Each object also referred to as an entry in a directory belonging to one or more object classes. An object class describes the content and purpose of the object. It also contains a list of attributes, such as a telephone number or surname, that can be defined in an object of that class. You can publish entries of different object classes under another object as shown in figure 1-2, where an e-printer object and a personal object is published under the organization ICME supply. That's it for now.